Hi everyone, this is Mrs. J, and today we're going to talk about antiderivatives. Alright, I have a warm-up for you guys to try, so please pause the video and hit play when you're ready to check. Alright, so go ahead and check your work. So remember, you can use your graphing calculator to evaluate a derivative at any point, so we don't actually need to find that derivative by hand, although we could for either one. So here f prime of 2 is approximately 109.196. That's the slope of our line, and the point is 2e to the fourth, because you have to plug it in to find the y value. And then you can just leave your equation in point-slope form, just like this. That can be your final answer. Same idea for part B. Use your calculator to find the derivative evaluated at x equals 2. Here's the point where you're finding the tangent line, and you can leave your equation again in that point-slope form. All right, so now that we know everything there is to know about derivatives, we're going to start working our way backwards. So imagine that I tell you that f prime of x is x squared. So this is the derivative of f of x. So now I'm wondering, well, what would f of x be? So instead of actually finding the derivative of f of x, here we have the derivative and we want to work our way backwards. So we can use our knowledge of our derivative rules. Here it would be like doing the power rule, but backwards. So if the derivative has a power of 2, we know that the original function would have a power of 3, because remember that comes out front, and then our exponent decreases by 1. But you'll notice that our derivative doesn't have any coefficient, or the coefficient is 1. So that means that we would need a value here that when I multiply it by 3, it becomes 1. So we can work our way and say, oh, it'd be 1/3 x, and you can kind of double check. If I were to find the derivative of this, I would do 3 times 1/3, and then it'd be x squared, which gives us x squared. So this process that we just did, just using logic, is actually finding what's called the antiderivative. So by definition, a function f is called an antiderivative of lowercase f on an interval y if f prime of x equals f of x. So the antiderivative is like working backwards, like you're starting with a derivative here and saying what would the original function be. So again, if you took the derivative of uppercase f, you would end up with lowercase f. So this process of finding the antiderivative is what we're going to start talking about today, and it's really what we devote a large part of next semester to as well. So now that we understand broadly what an antiderivative is, let's think back to that example that we just did and wonder, are there any other functions that can have that same derivative of f of x squared? So remember, we essentially said our antiderivative there was 1/3 x cubed. But imagine all of these other cases over here. If you are adding or subtracting a constant to this same function, when you take the derivative of this function, the constant turns to 0 because the derivative of any constant is 0. So actually, all of these functions have the same derivative of x squared. And in fact, there are an infinite number of functions that would have this derivative. So therefore, there is a way that we can write a general form of an antiderivative. So the most general antiderivative that we can give is in the form of f of x plus c. And we would actually write plus c where we know that c represents an arbitrary constant. So if you're ever finding a general antiderivative, we're always going to make sure to add that plus c at the end to take into account the infinite number of functions that really would have that same derivative. So that c value, we call c the constant of integration. Again, we'd just make sure to include it in our answer anytime we're finding what's called that general antiderivative. Now, sometimes we will be finding what's called a particular antiderivative where we're given maybe more information about the function, but anytime we're finding that general antiderivative, our answer should have that constant of integration. All right, so just a little more notation and vocabulary. So when we are finding the general antiderivative, we call this antidifferentiation or indefinite integration. And when we write it, we will use this integral symbol. So our expression will look something like this. We do the integral symbol, and then we write our function, which is called the integrand, and then we have this variable of integration, which shows what you're differentiating with respect to. And then this would equal our general antiderivative. So we have our antiderivative with respect to x, and we want to make sure to include that constant of integration. So I want you to think of integration as kind of like the inverse of differentiation. It's going backwards, and differentiation is like the inverse of integration because they kind of undo each other. So integration or anti-differentiation will be really common phrases that we will be using. All right, let's give a couple of these a try together. So here we're just finding the antiderivatives, so we're going to, again, just use logic and work our way backwards. So we have 4x cubed. So to find our general antiderivative, we know it would be like the reverse of that power rule. So that would mean we are starting with x to the fourth, and if we were to differentiate this, the 4 would come out front, and this would turn to a 3. And when we actually multiply the 4 to the constant, we end up with 4x cubed, which is what we want to end up with. So then all we need to add is that constant of integration, and we are done. And that is our general antiderivative. All right, let's try another one here. So here we're going to, again, be using that power rule, so let's work our way backwards. If we end up with x to the 1/2, that means that we started with x to the 3/2. So this would multiply out front, and we want our final coefficient to be 1. So we need a constant here where when we multiply it by 3/2, it becomes 1. So if you put 2/3 out front, 3/2 times 2/3 is equal to 1. And then all we need to add is that constant of integration. And again, we are all done. All right, let's try a couple more together. So here we have f of x equals 2 times the cosine of 2x. So to find our antiderivative, well, we know if we're ending up with cosine, we know, well, the derivative of sine is cosine. So we would have the sine of 2x, and if I were differentiating this, I would need to use our chain rule. So it would be cosine of 2x times the derivative of 2x, which is just 2, which is actually what we want, so we don't need to adjust our coefficient at all. But we do, of course, need to add our constant of integration, and then here we're actually done. There's our general antiderivative. And then for part B, we can kind of work our way through each individual term. So let's start with that 3 e to the x. So we know that the derivative of e to the x is e to the x. So if I want to end up with e to the x, I would start with e to the x, and we could have the constant out front because that won't change anything for our derivative. And then same thing for the second part, we can start with our constant. We say, okay, if we're ending up with secant squared, we know that secant squared is actually the derivative of tangent. So we have tangent of x, and then we'll add our constant of integration. So it will be really important that you can recognize those common derivatives like secant squared or e to the x to help you kind of work your way backwards. All right, let's try another one together. So here's the function that we're going to find the antiderivative of. And for this one, when you see something like this, it actually might be easier to rewrite the function, this function first. So I'm actually going to write it as 3 separate terms. And it's going to be much easier for us to anti-differentiate from there. So this becomes 5x to the negative 6, so 5 over x is 6. This will end up being negative 4x to the negative third because we have 4 over x cubed when you simplify. Here, your x to the 6 cancel out altogether, so we're just left with 2. So now, instead of finding the antiderivative of a quotient, I can just find the antiderivative of each of the individual terms. So let's start with that first term here. So remember, when we're using power rule, we would start with the number that is 1 more than this. So we'd actually start with x to the negative 5th. So we're essentially adding 1 to this. And then that would go out front. And if I want my ending coefficient to be positive 5, all I need to do there is put a negative out front. And then I will end up with negative positive 5x to the negative 6, so that's what we want. Now let's move on to this next term. So here I'm going to increase my exponent by 1 to work backwards. And then this would multiply out front. I want it to end up being negative 4, so I should have a plus 2 here, because negative 2 times 2 is negative 4, and then our exponent decreases by 1. And then for 2, well, we know that that would be start with 2x, because the derivative of 2x is just 2. So now we will want to make sure to add our constant of integration, and then we'll just write our final answer so there's no negative exponents. And then we are done. So if there's a way that you can rewrite the original or the function that you're given to maybe split it up into individual terms rather than a quotient or a product, I would definitely recommend doing that. So here is just a table of some what are called particular antiderivatives that you might find useful. So when you're starting with these functions, again, these are just the antiderivatives. Many of them are just kind of using logic and knowing what you know about your different derivative rules, but again, this might be useful to you. So here, this one is kind of the rule that we've been working with, doing our power rule backwards. Here, this one could be useful. Remember, 1 over x is x to the negative 1. So when you see that, you do need to remember, oh, the way I achieve that is from the natural log of x. The derivative of natural log of x is 1 over x. Here's a good one as well. If you want to end up with an exponential term like b to the x, we would start with b to the x over natural log of b, remembering that b is just a constant, so natural log of b is also just a constant. Because remember, the derivative of b to the x is b to the x natural log of b, so dividing by that natural log of b cancels it out, leaving you just with the exponential term. And then here we have some of our trig ones, especially these more common inverse trig functions. So again, you can refer to this table to help you, but it's really just using logic and working our way backwards from our derivative rules. All right, so now we're going to try finding what are called specific antiderivatives. So these answers will no longer have that constant of integration because we're given a little bit more information to help us determine what our specific antiderivative should be. So we will start by finding that general antiderivative. So we're kind of work our way backwards again. So here we would have just x squared, and the derivative of x squared is 2x. And then for this one, it may help if you rewrite your function like this. So it's 3x to the negative, or negative 3x to the negative 4th. So meaning we'll start with x to the negative 3rd, so we increase our exponent by 1. And if we want to end up with negative 3, oh, that's going to happen when I take the derivative. So here would be our general antiderivative, which we can write without a negative exponent. But here they're giving us more information about that antiderivative. They're telling us that f of 1 equals 0. So that means that I can actually substitute that point to help us solve for c. So I'm going to replace this with 0 and x with 1. And then we end up with c equals negative 2. So that would be our constant of integration. So once we know what that is, then we no longer have a general antiderivative, that we actually have a specific antiderivative. So it'd be x squared plus 1 over x cubed minus 2. So this will be our final answer. All right, let's try another one together where we're finding that specific antiderivative. So here, maybe you notice, or hopefully you start to recognize that within this function, we have that expression 1 over 1 minus x squared, and then it's times 4. So hopefully you recognize this as the derivative of arc sine. So when you're finding that antiderivative, it would just be 4 for that constant, and then times arc sine of x. And this is also in that table that we had a few slides ago that I said might be helpful. And of course, we need that constant of integration to start, and then we'll use this additional piece of information that f of 1/2 equals 1 to help us solve for c. So I'm going to substitute 1 here, 4 times the arc sine of 1/2 plus c. So we know that the arc sine of 1/2 is pi over 6. So we have 4 times pi over 6 plus c. So c is actually 1 minus 2 pi over 3. So that's our c value. So we're going to substitute all of this right here, giving us our specific antiderivative. So we'd say plus 1 minus 2 pi over 3. All right, let's try another one together. So here we're going to find the position function given this acceleration function of cosine of t plus sine of t. So first we need to do the antiderivative to find the velocity function, because we know the derivative of velocity is acceleration. So let's find v of t. So the way you get cosine is by starting with sine, is the derivative of sine is cosine. And we know that the derivative of cosine is negative sine. So if I want to result in a positive, I'm going to have to say negative cosine of t. And then, of course, we have plus c. Now here, with our first constant, we are given a piece of information about our velocity. We know that the velocity when time is 0 is equal to 5. So we can substitute that value, that coordinate, to help us solve for c, our constant of integration. We know the sine of 0 is 0, the cosine of 0 is 1, so we have 5 equals negative 1 plus c, so c equals 6. So our velocity function is sine of t minus cosine of t plus 6. But we need to do one more round of an antiderivative to help us find that position function, because we know that the derivative of the position function is velocity. So if we want to end up with a positive sign, we need to start with negative cosine of t. And then here we would have negative sine of t, and then here we'd have plus 6t. And then we do have another constant of integration. I'm just going to give it a different variable since we've already used c. I'll call it d. Now we do have an additional piece of information about our position function, so we can substitute that value to help us solve for d. 0 plus 6 times 0 plus d. So this is 0, so this will disappear, and we have 0 equals negative 1 plus d, so d is 1. So our position function, so our final answer, would be negative cosine of t minus sine of t plus 6t plus 1. And there you have it. All right, we're going to try one last example together. So here I have a baseball is thrown upward from a height of 2 meters with an initial velocity of 10 meters per second. Determine its maximum height. So that means that we are going to need to find a way to determine the position function. And the information we have, well, we know that the initial position is at 2 meters. We know s of 0 equals 2 meters. And we know the initial velocity is 10 meters per second, so v of 0 is 10 meters per second. And here, we're assuming this is all happening on planet Earth. This is the gravitational acceleration constant. We would either use 9.8 meters per second squared or 32 feet per second squared. So in this case, we'll use this one because our units are in meters. And this is the acceleration of any object that's falling on Earth. So this would actually be our acceleration function. We'll actually say negative 9.8. So then we can take the antiderivative of that, which would be our velocity function. So we have negative 9.8t plus c, our constant of integration. Then we can substitute this piece of information we know to help us find c. So our initial velocity is 10 times 0 plus c, so we can see that c is equal to 10. So here's our velocity function. And then we can take the antiderivative of that to find our position function. So s of t, again, it's going to be t squared. So we're going to need to divide this by 2 because we know when we take the derivative of it, we would move this and multiply it out front. So negative 9.8 divided by 2 is negative 4.9 t squared, and then we have plus 10t, and then I'll give us a new constant of integration. And then we're going to use that other piece of information here to help us solve for d. 0 squared plus 10 times 0 plus d, so we know that d is equal to 2. So here's our position function, 10t plus 2. So here we are actually going to be optimizing our position function because they are asking us to determine the maximum height. So there's a few different ways we could do this. We know that this is just a downward facing parabola. We know the maximum height will always occur at the vertex. But if we are going to use calculus to do this, we know that to optimize this, we would need to figure out when it is changing from increasing to decreasing to find that maximum point. So that means that we'd actually have to go back to our velocity function, which we solved for earlier. And then we would find our critical numbers here. So we have, we would set it equal to 0. So we have 9.8t equals 10. So t is 10 over 9.8, which we could just clear the decimals and then simplify from there if we want to keep it as a fraction. So that's our critical numbers. Of course, we should do our sign analysis to make sure that it's actually a maximum. So if you plug in any point to the left of this, you'll get a positive, and any point to the right, you would get a negative, which means that my position function is increasing here and then decreasing here. And since it is changing from increasing to decreasing, we do have a maximum at x equals, or t equals 50 over 49. Sorry, I left out the 4 right here. So that's the t value that maximizes our position function, but we actually want the maximum height, which would be the y value. So then you just need to go back and plug in 50 over 49 into your position function. You could use your calculator to get a decimal approximation here. You'll get 7.102 meters. So the maximum height is 7.102 meters, and this occurs when t is equal to 50 over 49 seconds. And there you go. So you can see a very common application that we could actually use anti-differentiation for. All right, so that's all for today's video. Thank you so much for watching.